So this is just taking the work that we have done with inclined plane and friction a step further. And what we're introducing here is Newton's law of motion. And we're also looking at D'Alembert's principle to solve this question. So let's get into some analysis and calculation. So just as a quick recap, let's just think about Newton's first three laws, where the first law we're thinking of an object remains in a state of rest, or it continues in a state of uniform motion unless it is acted upon by some externally applied force. So that's one law that we will consider when we analyze this question. And we'll also take the other two more common laws into consideration. The acceleration of an object acted upon by an external force is meant to be proportional to the force and is in the same direction. So that's the formula that we tend to see: force equals mass times acceleration. And then the last one, which everyone tends to be aware of, is for every force there is an equal and opposite reacting force, or for every action, equal and opposite reaction. Now let's analyze what we have here, and as we go through, I'm going to talk you through what D'Alembert's principle is all about and how we're applying it. So just as a quick recap then, what we have is an inclined plane. So we have this pulley system right there at the very top, and it's pulling this mass. Now this mass, in relation to the inclined plane, it will have a normal reaction. And this arrow that I'm just drawing the tip of, pointing upward, that's representing the normal reaction, which it's meant to be perpendicular to that inclined plane. Now, as a result of gravity, which you can see right here, mass times gravity, we get two force components from that force that's pulled on by gravity. And that force is Fg. So that's that force that's parallel to the inclined plane with respect to gravity. We get that force component, and we also get the component for this normal reaction there. And again, that's as a result of gravity. Now we have analyzed why this 30 degrees angle there is what it is. So just take it that, yeah, it's 30 degrees. So with that, let's do some calculations and analysis then. So what we have here, we have this 300 kilo block that is being raised using a cable and a pulley system, as mentioned before. Now the length of the slope is 40 meters long, which we'll take that into consideration in a sec, and it's accelerating at a rate of 2 meters per second square. So that's the rate at which the block is climbing the slope. Now it takes 2 minutes for the winch to pull the block, and the coefficient of friction we have there is 0.25. Now we're required to find three things. We need the tractive effort to get this thing moving. We need the work done, so force times displacement, spoiler alert, and we need the power required, so rate of work done, again, spoiler alert. Now let's do the calculations and the analysis. So the first thing that we can rectify here is the weight of the block. So we know its mass is meant to be 300 kilo. So if we just multiply 300 kilo by gravity, which is 9.81, then that's going to give us the weight. So that's the mass times gravity bit. And this turns out to be 2.94 kilonewtons. Or we can just write it as 2.94 times 10 to the power of 3. Now we have that. Let's consider the mg, the hypotenuse side of the triangle, and we have this 30 degrees right there in the middle, right there, that 30 degrees. And what we're going to do, we're going to use what we know now to be the weight, which is 2.94 kilograms, to find those two force components I mentioned earlier. So the first one is that n. And if we just think about our SOHCAHTOA bit, our trigonometry, then what we have is the hypotenuse, and we're trying to find the adjacent. So what that will be is just simply force, so 2.94 times by 10 to the power of 3 and cos 30 degrees, and that will give us the component for that normal reaction, and that is 2.55 kilonewtons, or 2.5 times 10 to the power of 3. The next one is our Fg, which that again is our unknown. So if we just do that Fg now, then it's the same idea. We have the hypotenuse and we're trying to find what our opposite side is. So again, that's just going to be sin. So if we use the same force there, 2.94 times 10 to the power of 3, only difference is this will be sin 30 degrees, and that will give us 1.47 kilonewtons. So that's two members down. So we have those two force components done. Now, from our previous videos, we talked about friction and we used the formula for friction. So we're going to have to use that again, the friction between the mass or the block and the inclined plane or the surface. So let's do that bit now. So for frictional force, I'll just use Ff. We just need to use the same formula that we had before, which is this U looking symbol that represents the coefficient of friction multiplied by our normal reaction, hence why we needed to find the normal reaction as well. So our coefficient of friction was 0.25 and our normal reaction was 2.55, so 2.55 kilonewtons, so times 10 to the power of 3, and that leaves us with, so that's 637.18 newtons, so that's a quarter of the total that's going to friction. So we're making some progress here. We have three force components. We have our frictional force. So what we need to look at now is what the total resisting force is going to be. And that's a good time for me to talk to you about what D'Alembert's principle is. It states that if the internal reaction to some form of acceleration or deceleration of a body is imagined to be an external force, then the body can be treated as though it were in static equilibrium under the action of, let's say, some system of external force. So what we are doing effectively is taking something that's moving and treating it as if it is static. And when we do that, we are then able to balance our force components, and as such, we can work out these unknowns that we're after. So that's why we now need to find the total resisting force, so that we know how much effort is required and how much power is generated. So let's find the total resisting force now. So for the total resisting force, this is just going to be a sum of those three forces that we just worked out. So first one being 1.47 kilonewtons, so times 10 to the power of 3, added to our 637.18, and this resisting force is equal to 2.11 kilonewtons. And you will notice something about this set of resisting force. It's all vertical based resisting force, so you will notice that. Now let's apply Newton's second law to understand what's happening with the force with respect to its acceleration, because we have that value for acceleration, which is 2 meters per second squared. So if we apply Newton's second law now, which is our force is equal to the mass times acceleration, then we know what force this thing is pushing based off of its mass and its acceleration. Its mass is 300 kilo and its acceleration is 2 meters per second square. So this force is going to be 600 newtons. Okay, so that's applying Newton's second law there. So what that means now in the direction that we are looking to go, its tractive effort is going to be a sum of the two forces that we just summed up. So let's find the tractive effort now. So that's the 600 newtons for the force with respect to mass and acceleration that we just found, and plus the total resisting force. So that was 2.11 kilonewtons, so times 10 to the power of 3, and that gives us a grand total of 2.71 kilonewtons for our tractive effort. So that's the total amount of effort required for this thing to get moving. Now let's see what happens with its work done, and we're talking about mechanical work done, so that will include some form of displacement. So everything will just fall in line now. The work done in this case is our force multiplied by displacement, because we have several variations of work done. This time around, we're taking the force and the displacement into consideration. So the force is the tractive effort. So that will be 2.71 kilonewtons. So times 10 to the power of 3, and we were told initially that the displacement was 40 meters, so times by that 40. So in terms of the work done, which is a form of energy, that's going to give us 108.4 kilojoules. So that's representing our work done. So just remember that we have several variations of work done, and it's all going to be contextual and similar to the next variable that we have here, or the next unknown that we have here, which is power. There are several variations of this one quantity, so just remember that it's in context to the question. So in terms of the power, it's just going to be work done with respect to time. So the work done was 108.4 kilojoules, so times 10 to the power of 3, and the amount of time taken in seconds was 120, or 2 minutes. So final answer then for the power required here is going to be 903.3 watts. So that's the amount of power required. We're going to continue to build on this concept, so if you find it valuable, then please consider subscribing to the channel. And until next time, the next video in our series is right here in the top right corner. I'll see you there.